Yeah, let me know if my screen is visible, that you're able to see what I am writing on the screen. Okay. Yeah, I'm assuming that my screen is visible. So yeah, let's begin. Okay. So good evening, everyone, and thanks for joining. Let's look at the assignment problems for week 2. Uh, I will give an outline about how to solve these problems. Um, right. Uh, so in the first problem, we are given collections of vectors, and we are asked to find out which of them is a basis of R2. Okay. So how do you in general solve a problem like this? Okay. So if a vector space is given to you, let's say for simplicity, the vector space is Rd, uh, then each vector in the standard coordinates or in any coordinate system, you can represent it uh, as these column vectors. Uh, right. Now, if you're given a collection of vectors, let's say V1 up to Vn, then in order that they form a basis, uh, n has to be equal to d. That is the first requirement. A basis is by definition a collection of independent vectors. It's a maximal collection of independent vectors. So maximality can only be achieved when the size of the set is equal to n. So the collection of vectors, which is a potential basis, that has to be at least d, or not at least d, that has to be exactly d. Right. So now if you are given away, so now is the independence check. So it is going to be independent if for all linear combinations of this form, uh, if for all you have each of these alpha i's to be equal to 0. Now, one of the ways in which you can check this linear independence would be as follows. So let's say each vector vi is basically some v, um, yeah, is v1i, then up to vdi. Then you can form a matrix. Um, form a matrix. So let me write it down. Form matrix A, um, where the I comma jth entry of this matrix is basically, so every column of this matrix is the corresponding uh, vector. So Vj, let's say this is the jth column, and the ith row would be the ith component of the jth vector. So that would be Vij, right? So you form a matrix of this kind. Now, once you form a matrix of this kind, uh, there are a number of ways uh, in which you can now solve this. Okay, so one of the ways is they're all equivalent actually. So so by saying that this thing does not have a solution, this is equivalent to saying that if you write an equation of this form, A alpha is equal to 0, where alpha is a vector over here. Okay. So if you write an equation of this form, then the only solution of this is equal to uh, then the only solution of this is equal to alpha equals all zeros. So alpha is basically the zero vector. Uh, so this is true if and only if the determinant of A is not equal to zero. Now, I hope you know how to compute the determinant. So computing the determinant would give it. Equivalently, this is same as saying that the rank of this matrix A uh, is going to be n. So in order to start computing the rank, you can do like you can reduce this matrix to what we call like anything to a row echelon form or a column echelon form. And because the row rank is equal to the column rank of the matrix, so let me write it down. Um, row rank of A is equal to the column rank of A. So reduce uh, A to row or column echelon form. Sorry. Right. So when you do that, just look at the number of zeros. If there are no zero rows or zero columns, depending on whether you did a row echelon or a column echelon form, if there are no such zero rows or zero columns, then the matrix is full rank, which is equivalent to saying that the determinant of the matrix is non-zero, which is equivalent to saying then that uh, the collection of vectors that is given to you uh, is uh, is indeed a basis. Okay. All right. I hope it's clear. Yeah, if there are any questions, feel free to ask me anytime. Now, going to the second problem. Right, the second problem is a very straightforward problem. So again, it's just pure computation. So let's say you are given two vectors x and y. Okay. Uh, in RD, and there is a notion of an inner product. So typically, I'm going to write this inner product. Uh, so typically, an inner product is often represented by these angular brackets. Uh, so this every inner product is actually a bilinear map. Uh, which will take two vectors x and y, and it will send it to their inner product, which is a real number. So they're going to be orthogonal, by which the definition of that means that the inner product of x and y would have to be equal to 0. So in this case, the inner product is defined as follows. It is defined as 4x1 y1 plus 5x2 y2. Uh, so can you confirm over here that this is a valid inner product? Uh, so is this a valid inner product?
Yes, sir. It is valid. Yeah.
Valid, right?
Yes, yes.
Yeah. Okay.
It can be applicable for complex. Actually, can be applicable for complex valued function as well.
Complex valued function. Yeah,
I
yeah,
mean,
it can be applicable. Yes, yes. In fact, um, yeah, um, you could, yeah, you could, but
complex valued vector plus. Yeah.
yes, yes, yes. But we are not going in that direction.
Oh, yeah.
We are restricted to reals. Um,
Okay.
so yeah, so one of the questions is that um, uh, if you're given two inner products, okay, so let's say I'm slightly deviating from this question, slightly deviating from this exercise. I'm trying to uh, answer this question. Um, just like a few things to keep in mind. Uh, so if you're given an inner product, let's say this is an inner product, and you're given another inner product. So let's say this is an inner product and this is another inner product. Okay. Now, if you're given two inner products, if you take a linear combination of these inner products, um, let's say you do like an alpha 1 of this thing plus an alpha 2 of this thing, then is it going to be a is it also going to be a valid inner product? Or under what conditions is this going to be a valid inner product? So notice that if you add two bilinear maps, it's going to be a bilinear map. So we are fine with that. Um, but there's another requirement for an inner product, which is that every inner product has to satisfy this thing, that on the diagonal of this thing. So by diagonal, I mean uh, so so the diagonal of RD is basically all points of the form X. Yeah, so the diagonal of RD is a subset of RD cross RD. Is basically all the points of the form X comma X. Now, the inner product has a requirement that every inner product uh, on the diagonal of RD has to be strictly positive, which is like inner products have to satisfy this thing, that if you take the inner product of itself with itself, it has to be like a norm squared. Okay. So it has to be positive. Okay. Now, if you plug this requirement into this thing, what we need is that for all x, uh, alpha 1 uh, x comma x plus alpha 2 x comma x uh, should be greater than 0. Okay. So it means that alpha 1 x1 norm squared plus alpha 2 x2 uh, norm squared should be greater than 0. Right. This has to be true for all x. Okay. Um, so in general, um, yeah. So in general, if alpha 1 and alpha 2 are positive, then this is always going to be true. So that's a sufficient criterion that if there are two inner products and if you take a linear combination of those two inner products, uh, uh, it's still going to be a valid inner product. Okay, so that was a slight deviation from the question. I hope this is answerable. This is a pretty easy question. Let's look at the third
Excuse me, sir.
problem. Yeah,
Uh,
someone.
yes, yes, sir. Sorry
Yeah,
for interrupting. Is
please go
this a
ahead.
sufficient condition for valid inner product? That
Yeah, it's a
if
sufficient
alpha 1,
condition.
alpha 2 are positive,
Both
then
positive.
only
Yes.
linear combination of two linear product is again inner product.
No, then not then only, because then only means that it becomes a necessary condition. It's not a
I mean,
necessary condition, it's a sufficient condition. Yes.
yeah, sufficient means that if alpha 1 comma alpha 2 are positive,
Yes.
then the linear combination of two inner products is again inner product. That is what you were saying.
Yes. Then you are
Yes.
guaranteed that it's going to be an inner product.
Can you give an
So
example, sir? Like,
yeah. Okay, so let's take an example. So let's take an inner product. Okay. So let's define. So let's say my vector space is R2. Okay. And I define an inner product one where the inner product between two vectors uh, um, x1 comma x2 uh, and y1 comma y2 is equal to x1 y1. Okay. So basically what this inner product does is that it does nothing with the x2 y2 components. It just takes the first component and does this. And another inner product is same x1 x2 y1 y2 uh, goes to x2 y2, right? So now let's form an inner product, which is this. Which is the inner product that's given to me. Okay. Right. So let's look at the third problem. So x and y are again two vectors, this time in RD. And right. Okay. And so there are basically some questions asked about the orthogonality of U and V. So U is x plus y and V is x minus y. Uh, okay, so let's do U comma V. Um, so U comma V is x plus y comma x minus y. So that is equal to uh, from the bilinearity of the inner product, that is equal to x comma x uh, uh, sorry, plus x comma minus y
so
plus,
please don't give the exact answer.
sorry.
Take it. Please don't give the exact answer because as you have considered
No, I'm
the
not going to
exact
give you the
vectors from the question.
I'm not going to give you the exact answer. Don't worry. And plus y comma minus 1. Okay. Right. So because this is an inner product on a real space, so the inner product is always, so the inner product is also symmetric, which means that uh, x comma y is equal to y comma x. Okay. So there's a minus term over here, which pops out, and these two terms would get cancelled. Okay. And it turns out this is equal to x comma x minus y comma 1, which is equal to norm of x squared minus norm of y squared. Right. Now, well, there are certain questions on orthogonality. Um, um, yeah, which you have to answer. I'm not going to give more on this question. All right, let's look at the other problems.
Inner product is conjugate symmetry, sir. If the domain is complex vector space, then it is a conjugate symmetry. If it is the domain is real vector space, then it is a symmetry. This is
Yes,
not
yes.
always true.
Yeah. So whenever I'm going to give statements, it's always going to be, unless I state otherwise, the field is always going to be real numbers.
And vector space, real vector
Because
space. Over the field, real.
yeah,
Okay.
all vector spaces here are real vector spaces, unless otherwise explicitly stated.
Okay, sir.
Okay. uh, Okay, let's look at this problem. I think we briefly did these two problems last week, but going to do this again this time. Um, yeah, so X and Y are two vector spaces, um, and there's a product defined on RD. Um I think someone had a question last week about these being column vectors, and so a column vectors, so there's a natural equivalence between column vectors and vectors in RD. So assuming that you take the standard basis, every vector in RD would have like d components to it, or yeah, d components to it, or d coordinates. Those coordinates can be arranged in the form of a column matrix. So there's a natural so the natural equivalence between uh, column vectors uh, and d cross one matrices. So let me just quickly write it down. So right. So let um, R d comma one denote d cross one column vectors or column matrices. Then each of these represent uh, coordinates of vectors in RD and vice versa. Yeah, so we're going to use this interchangeably. Sometimes we're going to write this as a column matrices, sometimes we're going to just treat them as vectors in RD, etc., vice versa. So yeah, there are two questions. Which of them is actually true? Yeah, you have to actually solve um, all of these. Um, so if given two vectors, then the if you do if you explicitly solve this, so that is equal to the norm of this space, or rather the norm of this vector, two norm rather. So that is equal to, of course, x11. And of course, what this is, it's clear what this is. This is the inner product. Yeah, so should be answerable. Now looking at this problem, the ninth problem. Yeah, so there is a vector given 1D rather, which is uh, which is a column matrix with all ones. And yeah, it's basically evaluating all these options. The way you answer this kind of problem is that you evaluate all these options and then you check which of this is identically true. Okay. Um,
Is this question single option question or multiple option question, sir? This
I don't know.
which of the
I mean, you
following
would know.
statements is true means single option question only, no, or multiple answer. Which of the following
The way I
statements
look
are
at this is
means
that there are more than one options which are correct over here. No, no, it's a single option correct answer. It's single option correct. Yeah.
okay.
Yeah, all these problems, at least up till now, all these assignments are single problem assignment. So, um, yeah, so there is this vector that is given. So in general, this is not a standard notation. So if you have a vector x in RD, it's not this is not standard notation to represent this in this way. But okay, it's given. Uh, it's given. Note that each of these xi's would have to be positive or non-negative rather for this thing to make sense. And well, now if you take the norm of this guy, that is equal to x1 plus xt. Okay. So just like a quick tip over here. So so in linear algebra problems, it is helpful if you can quickly understand um, if you can quickly understand certain forms that are given to you, and if you can quickly translate between the various equivalent notions. So in linear algebra, there are various equivalent notions of expressing the same thing. Okay, so so one quick tip to note over here is that if let's say x is some vector and you're writing something like this. You're writing an expression of this kind, alpha 1 x1 plus alpha dxd. Okay. Uh, yeah. So then it is, so one way to look at an expression of this kind is to look at it this way. So consider this is to write it as a product of two matrices. So you can write it in this way. Consider this row matrix XD and this column matrix uh, alpha D. So this is equal to this if you just evaluate uh, the two the matrix product. And notice again that uh, that this is equal to, so if you assume the standard inner product on RD, so by the standard inner product on RD, I mean that the inner product where you just take the sum of the products of the components. That is the standard inner product on RD. So if you take the standard inner product on RD, then this expression, which is basically equal to x transpose alpha, is equal to x comma alpha. Okay. So whenever you see like a linear combination of this thing, uh, it's also kind of useful to think of such a linear combination as coming from an inner product. Now this would be useful when later you see more and more examples in orthogonality, because because a linear combination like this equal to zero is equivalent to saying that this inner product is equal to zero, which is equivalent to saying that the two vectors are orthogonal. So yeah, so one quick thing like this to keep in mind. Okay. Um, right. Yeah, so what is this? You will notice that this is equal to nothing but the inner product of x with this vector, because these are all ones over here. Okay, right. Okay, just give me 1 minute. I'll be back quickly. I need a quick break. Okay, I'm back. Okay, so let's look at the remaining problems. Starting with this one.
Excuse me. Hello.
Yes. Yeah.
This is a problem solving session. You select problems of your own choice, need not be problems in the assignment, and solve the problems completely and tell us the concepts involved so that it will be of more useful to us. Just indicating the outside things and other things will not help us.
Okay, so I think you were there in the last session. I think
Yes,
there was an overwhelming request from what I remember in the last session,
yes,
where the what the students wanted was something like an outline about how to solve the assignment problems without actually giving out the solutions to the problems. So we decided that for a certain let's say the first 1 hour of the session would be dedicated to that, where we give an outline about how to go about solving the assignment problems, and the remaining part of the session could be dedicated uh, to taking up individual problems, maybe explaining some concepts, or giving out, or I can give, I can give some problems by myself. So there was this request from the group in the last session. So I think so that's why I'm proceeding in this way. Okay. Um, I will finish this part. There are four more problems to look at. Um, I will finish this part, and then we can look at different problems. Yeah, then we'll look at some different problems uh, where we look towards complete solutions. Um, these are complete solutions, by the way. So I guess I think you asked something like and explain the concepts. So and I'm asking this in a I mean, don't take it otherwise. I'm asking this in a very in a very inquisitive way. I want to know. So, where in particular do you feel that uh, there are concepts that that I'm skipping? I think I'm elaborating the problems. But is there any particular problem or any particular step where you felt that I'm skipping a particular concept, or I'm not going deep into it? Then let me know. Okay. Yeah, let's look at this problem, the fourth one. Uh, okay, so let's say we're given a combination of a linear combination of orthogonal vectors. So let's say our space is Rd, and we are given a linear combination of orthogonal vectors, say alpha 1 to alpha k. A, of course, let's say. So let's say this is a collection of orthogonal vectors. A quick question, why should k be less than or equal to d? Why, like, is it possible that k is greater than d? Is this possible? So if alpha 1 to alpha k is a collection of orthogonal vectors, is it possible that k is bigger than d, where d is the dimension of the space?
No, sir. Actually, the cardinality of linearly independent set should not exceed the dimension of the vector space.
Okay. And so is alpha 1 to alpha k a linearly independent set?
Did they? Are you assuming, or
Yeah, I'm
I don't
assuming that
understand?
they are orthogonal. They're orthogonal to each other. Then is it a linearly independent set?
Every orthogonal set need
Yes.
not be linearly independent.
Okay. So no, that's not true.
Every orthogonal set is linearly
Every
independent.
orthogonal set has to be linearly independent. Let's see why.
Okay. Okay. Okay.
Um,
Yeah.
yeah. So if you give me any orthogonal set, like let's say this one, and I write a linear combination. Let's say I write C1 alpha 1 up to CK alpha k, and if this is equal to 0, so I want to find a linear combination which gives this equal to 0. Uh, so then what I do is that I take the inner product of this with each of these alpha i's. So I take inner product of this with each of the alpha i's. Okay. Now if I take the inner product of this with each of the alpha i's, uh, with, let's say I take the inner product with alpha I, so then this is equal to C1 alpha 1 comma alpha I plus Ci alpha I comma alpha I, and then the remaining ones, Ck alpha k comma alpha I. Oh, sorry. Okay. Now by definition, or not by definition, by assumption, these are orthogonal to each other. So alpha I, alpha j is equal to uh, 0 if I is not equal to j, and it is a positive number. So let me write it in this way. So this is equal to 0 if I not equal to j, and it is positive if I equal to j. So if you take this, then all of these terms would vanish. Uh, the ones not equal to I over here and the ones not equal to I over here. And you get something like Ci uh, alpha I inner product, which is equal to norm of alpha I squared. Okay. Now this you have taken to be 0. So you've taken the inner product of this with 0. So this is equal to 0. And if we equate this side, this is a non-zero vector. So this is always, so its norm is always going to be positive. So that means that Ci is equal to 0. And this is true for all I. Okay. So which means that if you take an orthogonal set and you want to produce a linear combination which gives it 0, then uh, you can only do with the trivial linear combination. That is, you have to set each of these to be equal to 0. Okay. Yeah, so every orthogonal set is always going to be linearly independent. And because a linearly independent set can be at most the size of the dimension, so k has to be greater than or equal to, sorry, k has to be less than or equal to d. This is not true. Okay, so right. So now if you have a collection of linearly independent vectors, and you form some vector alpha, which is a linear combination of these vectors. And we ask you the norm of alpha squared. So that is equal to alpha times inner product of alpha with alpha. Right. So this is equal to C1 alpha 1 up to CK alpha K. Right. So this is a bilinear. So the inner product is bilinear. And so you can write it in this way. I think someone asked something in chat. Just give me 1 second. Okay, the material, someone is asking that the material is not posted. The material is actually posted. Uh, so I have a pinned comment. Uh, uh, you can go to this, you can go to my YouTube channel. Where the video is posted. When it comes to the sheet, there is a problem with the it's a logistics issue right now. So I'm not able to have edit access to that sheet, which is why I was not able to, or I was not able to update it soon. Yeah, hopefully that will be resolved soon. Um, right now, because of a logistics issue, I'm not able to have edit access to the sheet. So that's why I mean every lecture, every session would be posted that day itself. So this is the YouTube link. Please go to this YouTube link. You will see all the sessions there. Um, yeah, and once this logistics issue is resolved, I will start updating the sheet with the session links. Okay. Right. So going back to the problem, so the so if you expand this thing, this turns you will this is equal to there's a sum over two component or over two indices. Uh, One is I and the other is J. Both are from 1 to D. Same for J. And this is equal to Ci Cj alpha I comma alpha j. Now, if alpha I and alpha j are orthogonal to each other, then you know what these are, right? Um, if I is not equal to j. And so you have to plug this thing in this expression. Okay. And if you plug this thing in this expression is equal to this, because all the terms in which I and j are not equal are drop to 0. So you are left with uh, oh sorry, you are left with this term. Okay. So if you look at this result, it's very interesting um, because uh, because um, because if you look at, let's say, the standard inner product on RD, sorry, the standard norm on RD, um, the standard norm on RD is given by sorry. So the way you so the way we arrive at this standard norm in RD is as follows. So the standard coordinate vectors in RD. So if I quickly draw RD, this is R3, but think of this as RD. Um, when we write a vector x as something like this, uh, I hope you understand that this is actually a notation. Um, the notation is with respect to a fixed basis. And the bases that we generally consider are the unit vectors pointing in the direction of the axes. So there are these unit vectors which we often write as E1 up to ED. And when we write X as a column matrix, implicitly we are assuming that the basis that we are dealing with is the standard basis. So actually, this vector X in an algebraic form can be represented as X1 E1 plus XD ED. Now, the standard norm that we have on RD on Euclidean spaces is that we take these unit vectors pointing in the direction of the axis to be uh, orthogonal. So we take each of these EIs to be orthogonal. So this is 0 if I is not equal to j, and we take and their norms are equal to 1. So EI, comma EI is equal to 1. So with this notion, if I compute the norm of x squared, okay. So the norm of x squared would be equal to x1 squared E1 comma E1 up to xd squared ED comma ED. Because as I said, these are each of these unit vectors are orthogonal, which is actually equal to x1 squared plus xd squared. So the norm, the standard norm that we have uh, on the Euclidean space um, is actually coming from this identity. Okay. Okay, let's look at the fifth problem. Um, okay, suppose U, V, and W are linearly independent vectors, uh, and T is a linear injective function. Okay, so let's look at this question 5. I'm going to use this space over here. Okay, again, this is like a generalization of the problem. So if you're given a collection of vectors U1 to UK, which are linearly independent, and you're given, let's say, a
Sorry, you are muted. Please unmute yourself.
I accidentally got muted. All right. Okay. Yeah. So let's say, yeah, thanks for telling me. Yeah, let's say there are a collection of linearly independent vectors, and we have this linear map T from Rm to Rn, and T is a linear injective map. Okay, so let me ask a few questions first. So if T is a map from Rm to Rn, what can we say about M and N? Let me ask this question. Uh, what can we say? Yeah, feel free to answer. I'll be waiting for answers to this. Yeah, please unmute yourself and give me the answer to this problem. What do you think? If T is a linear map, which is an injective map from Rm to Rn, what can you say about M and N? I mean, in particular, let's say Rm is R3 and Rn is R2. Is it possible to have a linear injective map from R3 to R2? Okay. Someone said that uh, M is equal to N. Okay. Uh, let's let's take this option. Um, yeah, but is it possible that M is smaller than N? Is it possible that M is bigger than N? Is it possible to construct a linear map from R3 to R2, which is injective?
Oh, it's I think
Yes, please go ahead.
it's not possible.
Not possible. Okay, okay. So in general, if the domain has a greater dimension than the target space, then is it possible to have a linear injective map between Rm to Rn if M is bigger than N? Well, the answer to that is no, it's not
Linear is
possible.
okay, sir. Linear can be done, but yeah, it's not possible. Yes.
Yeah, I'm talking about linear maps only. Yeah,
Yeah, of course, it is linear.
and it's not
When we talk
possible.
about the injective, it is not possible.
Yeah, it is not possible. So let's see why it is not possible. So the answer to this is M is either equal to N or M is smaller than N. In general, if the domain is a smaller if the domain has a smaller dimension than the codomain, then and only then is it possible to construct linear injective maps. If the domain is bigger, in the sense that it has a bigger dimension, then it's not possible to have a linear injective map. And I'm going to give you a very intuitive reason. The intuitive reason is as follows. So if you look at Rm has a basis which has m independent vectors. So let's say if you take some basis B, it will have m independent vectors in it. Okay. And something like Rn uh, can have at most um n linearly independent vectors. Now, if m is bigger than n, what you require to do in order to construct a linearly independent map is that um, you have to take this basis, which has m elements, and send it to a linearly independent set. But a linearly independent set can have at most n elements in Rn, and n is smaller than m. So basically, I'm looking at this case where m is bigger than n. Uh, but you cannot have uh, 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 basically if I take these m elements and if I send them to Rn via a linear map T, then you'd have m vectors. But m vectors cannot be linearly independent in Rn because n is smaller than m. And this is the reason why it's not possible to construct linear injective maps from a higher dimension to a smaller dimension. So if you want like a proof of it, the proof is basically as follows. Um, so if T is a linear map from Rm to Rn, then when we say that T is a linear injective map, that is equivalent to saying that uh, someone asks me, can we assume all the can you assume all the 12 sessions we to follow the link? Yeah. The my YouTube channel remains the same. So yeah, they will be posted in sequential order. So yeah, everything in that channel. Okay, so T is a linear injective map. This is equivalent to saying that uh, if T of x is equal to 0, that implies that x is equal to 0. Um, why is that? Because what is a linear injective map? So if we say that something is a uh, linear injective map, then it means that if you give me two distinct x and let's say an x prime, then T of x is never equal to T of x prime because it's an injective map, right? Now, because it's an injective map, uh, what this means is that T of x minus x prime is not equal to 0. So if you give me some vector y, okay, such that T of y is equal to 0, of course, T of 0 is going to be equal to 0, then this means that y is equal to 0. Okay. Alternatively, if this criterion is true, that T of y equals 0 implies y is equal to 0. If this criterion is true, then it implies that it is a linear injective map. Why? Because if T of x were to be equal to T of x prime, then that implies that T of x minus x prime is equal to 0. And this implies that x minus x prime is equal to 0 or x is equal to x prime. Okay. So T being a linear injective map is equivalent to this condition. Okay. Now, let's say you are given a collection of linearly independent vectors. Uh, let's say U1 to UK is a collection of linearly independent vectors. Then what can we say about TU1 up to TUK? So so when I write something like TU1, this is like a shorthand notation for writing T of U1. We often omit this bracket and just write it as T of U. Okay, so is this going to be linearly dependent or linearly independent? So typically when you are asked to prove something like something being linearly dependent or something being linearly independent, what we often do is, let's say you are asked to prove that something is linearly independent. You often assume the contrary and you try to say, okay, what if this was linearly dependent? If this was linearly dependent, then I can produce a linear combination which gives me this 0. And this linear combination is a non-trivial linear combination. So here also let us assume that there exists such a linear combination such that this kills off this collection. So which means that I can find vectors or which means that I can find these scalars C1 up to CK such that C1 TU1 plus CK TUK is equal to 0. Okay. Now T is a linear map. Okay. Because it's a linear map, every linear map satisfies this property. T of CU is equal to C of TU. Okay. So you can write this expression as equal to T of U1 C1 plus, sorry, T of C1 U1 plus CK UK is equal to 0. Now T is a linear injective map. So if this is equal to 0, that implies that this has to be equal to 0. This has to be equal to 0. but it is given to you that you want to UK are linearly independent vectors. So if they're linearly independent vectors, then if this were to be equal to 0, the only possibility is that each of these CKs, each of these CIs are equal to 0. Okay. So what this means is that linear injective maps will always send uh, linearly independent vectors to linearly independent vectors. So it will send a linearly independent set to a linearly independent set. And that is the reason why you cannot construct a linear injective map from a space with higher dimension to a space with lower dimension. Okay. Yeah, yeah. Hope this is clear. All right. Yeah, let's look at the seventh problem. I think the sixth problem is pretty easy. I think this is like a very easy problem. I'm not going to solve this problem. Um, let's look at the seventh problem. The seventh problem gives us what is the range for this expression that they have given. So I'm going to write an inequality, which is called the Holder's inequality. Um, Right. So Holder's inequality, what it basically says is that okay, yeah. Right. So what this inequality says is that okay, someone's asking, can't this be treated as inner product of two unit vectors and proceed? Which this one? This one? Yeah, I think the answer is okay. Yeah, you can think of this as the inner product of two unit vectors. Yeah. You can treat this as inner product of two vectors because of this reason. Okay. Um, so if you so this well, what is this? This is equal to x inner product y and divided by the norm of this and norm of this. Okay. So because inner products uh, that's what I'm trying answering. Yeah. Um, so you can absorb this over here. So I mean, you can write this as equal to this x by norm of x, comma y by norm of y. But this is a unit vector. This is a unit vector. Uh, so this is equal to uh, some x prime, comma y prime. Where each of these are unit vectors. So this problem, uh, uh, you can always, it's basically asking this question that if you give me two unit vectors, what is the maximum and minimum value? Let me just write it over here. Um, given two unit vectors, alpha and beta, what is the range of values of of this guy. Okay. Um, right. So someone asks me in chat, I feel it is simply the cosine angle between them. Yeah, I mean, that's fine. You can use that intuition here, but it's important to have it's important to know one thing, that there's no such notion of cosine in higher dimensions. So if this is RD and D could be anything, let's say D is 10. I mean, what is the notion of cosine between two vectors? Okay. Uh, you can think of it in this way and then proceed. And if you think of cosines, then you know what is the range of the cosine. But this is that's not a fully rigorous way of answering this problem. Okay. So in order to fully rigorously answer this problem, you need like a more algebraic. Is it said it's D based on D equals 2? Let me see. No, it doesn't say that D is equal to 2. If you look at the seventh problem, it says let xy belong to RD. It doesn't say anything that D is equal to 2. Okay. Yeah. I mean, you can think of it in cosine, but there's no such notion of cosine in hard dimensions. In fact, the notion of cosine is in fact defined in this way. So if you have a if you have so I will okay, let me actually talk about this problem a little bit. Um, there is, let me write it in this way. There is no canonical notion of cosine in RD. Okay. The way we define cosine between two vectors. So if you give me two vectors, u and v in RD, then you can define something like a cos between the two vectors, and this cos theta is defined in this way. It is defined as u comma v by norm of u times norm of v. Okay. Uh, so what you are saying is that, oh, this is equal to the cos of this thing, and I know the range of cos. So I am going to give you the answer to be whatever the range of cos is. But that's not correct, because cos itself is defined in this way. The cos of the angle between theta, whatever this angle is. So if you are given two vectors x and y, then the angle between these two vectors u and v is basically this is basically the cosine inverse. So it's this thing. Um, okay, now you can define this cosine inverse only because the range of this expression is within the range of cos. So this expression always would be between these guys. Okay, and that is the reason why you are able to define an arc cos. So you cannot use this to say that oh, this is going to be the cost thing, because it's like putting the cart before the horse. It is the definition of this. Okay. So you need like an algebraic notion to solve this. I guess there can be multiple ways of solving it, but let's see. So let's take u, write this u in as this vector u1 to ud in the standard basis, and v as equal to v1 to vd again in the standard basis. Now it is given to you that each of these, so essentially solving for the range of this is equivalent to assuming that u and v are unit vectors. So you have u1 squared up to ud squared is equal to 1, and v1 squared up to vd squared is equal to 1. So now you have to compute the range of this expression u1 v1. Yeah, but uh, no, but it doesn't prove. I mean, okay, how did you arrive that the range is -1 to 1? How did you arrive at this thing that the range is -1 to 1? Okay, someone says that sir himself gave expression in the lecture. Okay, okay, fair enough. Um, but let me still complete this just for the sake of it. Um, Yeah, I mean, you will see that this expression is going to be maximized or minimized uh, if um, if v is of the form that exactly one of the components is equal to 1. So there's exactly one component equal to 1. The rest are zeros. And u is again exactly the same component is equal to plus or minus 1. And the rest are 0. So that's when this expression is going to be maximized or minimized. All right. I think that concludes all the problems. Yeah, sorry, I'm not going to look at the um, yeah, okay. I guess it was already discussed in class, so yeah, there's no point going too much more into it. Okay, so that concludes all the problems from week 2. Yeah, If you have further questions or any particular concepts that you want me to, uh, or any particular style of problems that you want me to uh, especially look at, I can do that during this time. We have about half an hour left.
Relationship in the, say, some properties.
Hello.
Yes, yes, sir. Hello, can you hear me, sir?
Yeah, yeah, yeah. I can hear you. Just give me one. Just give me 1 minute. I'm looking at one thing. Yeah. Please go ahead. Ask your question. Yeah, please ask your question.
Relationship.
Your voice is a bit low.
Fine.
Can you increase your
Yeah,
volume?
yeah.
Yeah.
Is there a relationship between the affine function and the linear transformation? And please give some
Sorry,
real
ask
life
again.
examples.
Say that again.
Uh, I'm asking the relationship between affine function and linear transformation.
Okay.
And give me
Okay.
some, if you know some real life example, just please
Ha,
explain.
ha, ha, ha. Yeah. Okay.
Every time you are asking twice. I don't understand. You're not
Sorry.
audible. Whenever I
Hello.
ask a question, sometimes you ask, repeat again or something like that.
Yeah.
Don't know
It's
whether
to
you
do
are
with the
intentionally
volume.
asking or something.
Sorry, what?
I don't know whether you are intentionally asking or you are really not uh, listening. I mean, my voice is not clear to you. Or okay, no problem,
No,
sir.
I mean now your voice is clear, but when you were asking the last time, your volume was pretty low.
I don't understand. Okay, no problem. Please.
Okay. Yeah, let me answer this question and then I'm going to give a set of problems which you can try as homework. Um, and then uh, uh, maybe next time we can discuss those problems. Okay. Okay. What is a linear map and what is an affine map? So an affine map is basically uh, a combination. It's basically uh, okay. So let me write it in this way. So let A from RD or from Rm to Rn be an affine map. So an affine map satisfies this property. So what does a linear map satisfy? So a linear map satisfies this property. So if T is a linear map, then a linear map satisfies this property that T of alpha x plus beta y is equal to alpha times T of x plus beta times T of y. So a linear map distributes over linear combinations. An affine map distributes over affine combinations. So what is an affine combination? So given x and y, we say that alpha x plus beta y is an affine combination if uh, if alpha plus beta is equal to 1. Okay. So an affine map will distribute over affine combinations. So in other words, A of alpha x plus beta y, provided alpha plus beta is equal to 1, this is equal to alpha times A of x plus beta times A of y. So an affine map typically looks, an affine map, not typically, that affine map will always look like this. A of x is equal to some linear map T, and then there's some offset. So an offset, you can think of this as some Z. Okay. And now if you do this affine combination, if you write A of alpha x plus beta y, that is equal to T of alpha x plus beta y plus uh, wait, I think I'm making a mistake somewhere. Just give me 1 minute. Stay. Yeah, so this is equal to this plus z. Um, so this is equal to alpha times t of x plus beta times t of y plus z. But this z, you can write it as alpha t of x plus beta t of y plus alpha z plus beta z. Because alpha plus beta is equal to 1. And this is equal to alpha of a of x. You take this term plus this term, and beta of uh, a of y. Okay. So, like a standard example of a like I said, you this is the blueprint of an affine map. So, an affine map always has two pieces of information to it. It has a linear map and it has a vector. Okay. So, any linear map and any vector will define an affine map. So let me write it down. Any linear map and vector defines an affine map. So let's take a concrete example. Um, let's say you have a map A from R3, sorry, from Rn to R. Which is given by this. So A of x is equal to uh, x1 plus xn plus 1. This is an affine map from Rn to R. Right. Now, if you want a map from an affine map from, let's say, Rn to Rm, say, then you can basically stack up m. Just let me write it down in this way. Stack up uh, m affine maps. Alternatively, but equivalently, you can take any map from Rn to Rm. So, what is a map from Rn to Rm? Like, what is the easiest way to construct a map from Rn to Rm? Just take a matrix. So, construct an n cross m matrix. Um, so, construct a matrix. Um, let's call it C. From Rn to Rm. It could be anything, any matrix of your choice, and take any vector z in Rm. Then this linear map, this map is going to be an affine map from Rn to Rm. Okay. Um, so let me now give some questions on affine maps, um, which I would expect, which you can try. Number one, let alpha, beta, and gamma be yeah. So the recording is already uploaded. Uh, please look at uh, please look at the YouTube channel for the uploaded recording. The sheet is not uploaded. The sheet is not updated because there's a logistics issue. I'm still I do not have edit access to the sheet. So as and when it's resolved, I'll also update the sheet. But you can go and check out the channel. It's all the sessions would be uploaded to this channel uh, in sequence. Okay, so let me complete the question that I was asking. So let alpha, beta, and gamma be collinear vectors. And A, so these are all in some Rm. And let A from Rm to Rn be an affine map. Prove that the image vectors, that is A alpha, A beta, and A gamma, are also collinear. Second problem, let S, a subset of Rm, be a convex set. Show that or prove that uh, the image of this set under this map A, that is A of S, is also a convex set. Yeah. Yeah, this is like an exercise problem that you can think of. Okay, otherwise, let me give you some problems. These are slightly advanced problems. It's still worth giving the try. Hmm. So I'm going to define a vector space. And this vector space is defined as follows. So the vector space is Pn of x. So Pn of x is the space of all polynomials in x of degree less than or equal to n. First is, uh, sorry. Yeah, this is one question. This is another question. Yeah, first is to show that Pn of x is a vector space. Okay. So next what I do is I define an inner product on Pn of x. We define an inner product on Pn of x as follows. If f and g are two polynomials in Pn of x, you define the inner product as f times g dx 0 to 1. Either 0 to 1 or you can take it minus 1 to plus 1. Show that uh, show that uh, this is a valid inner product. Okay. Okay. Um, the next problem is this. It's a subpart of this problem. So I'm going to define a linear map T from Pn of x to Pn of x, which is defined as follows. So if you give me a polynomial, um, let's say f is a polynomial and the uh, f is fn x bar n plus f1 x plus f0, then I define a linear map T of f, which what it does is that uh, it does the following. It sends this polynomial um, to this polynomial fn minus 1 x to the power n plus fn minus 2 x to the power n minus 1 plus dot 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 f2 plus dot 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 um, uh, plus f1 x let me repeat the question. There's this linear map TF, uh, which if you give me a polynomial, uh, fn x power n plus f1 x0, it basically rotates the polynomial. So if this was fn minus 1 up to f1 f0, then it rotates it. So it sends this coefficient to this to this to this to this, and this over here. Okay. So this is a linear map from uh, Pnx to Pnx. So you have to investigate T. Is T a linear map? Uh, is T an injection? um, is T a bijection? So these are the problems that you have to answer. So notice that this is one of the vector spaces that we are dealing with, uh, where the um, where the space that you're dealing with is not Rn. It's a different kind of a space, but it's a vector space still. Okay. And give one more problem. Before we wrap up. Okay, let's finally wrap up with this question. Um, so the vector space that we're going to consider here are 2 cross 2 matrices. Um, so V is basically R 2 cross 2. So we're given a matrix B, which is equal to uh, 2 minus 2 minus 1 comma 1. Now I'm going to define a map from R2 cross 2 to R cross 2 cross 2. And this map is just post multiplication with B. So it takes a matrix A and multiplies it with B. Okay. So let A, okay, so let to define some subspace. So let uh, um, so let W be the subspace of R2 cross 2, which consists of all the matrices A such that AB is equal to 0. Okay. What is the dimension um, of um, of W? Basically, W is the null space of this linear map. What I'm asking you is, what is the dimension of this null space? Okay, so these are three problems to think about. One is on affine maps. One is on vector space of polynomials, and one is on this vector space of matrices. Yeah, I think we're at the end of the session. If you have any concluding questions, you can ask me, and then we can wrap up otherwise.
Sir, in third question on the
Yeah.
linear transformation.
Third question, this one. Yeah,
Yeah,
go ahead.
P is a linear transformation from set of all polynomials of degree less than or equal to 2 to same polynomial. You define linear transformation is in this manner. So
This
I think
part,
here
this part you're
both,
talking about, this subpart?
yeah, third part, yes, sir. Yes.
Yeah, yeah, go ahead.
I think here dimension of domain and codomains are same.
Yeah.
Hence, we no need to check all the three conditions of bijective. It is enough to check only either it is injective or enough that confirms automatically
Yeah.
bijection. Is
Yes.
it true or
That's true. That is true. That is true.
I think it's linear map and injective, bijective. All three are correct.
Yeah. Okay. Okay.
Previous vector
And
spaces, yeah, that is standard example of question number 2. It is the standard example of vector spaces. I think that is also fine. True.
which one? Which
What
question?
that set of all polynomial less than or equal to 2, less than or equal to n.
Yeah, yeah, yeah. It
Yeah,
is a vector space. Yeah,
it's a
right.
vector space, and that the inner product also valid inner product. It satisfies all the properties
Yeah.
of an inner product.
Right. So if it's a valid inner product, can you find out an orthogonal basis of with respect to this inner product?
Orthogonal basis?
Yes.
Normal basis
You can always find out an orthogonal basis. Do you know about the Gram-Schmidt orthogonalization process?
Yeah, orthonormalization, so not orthogonalization. Yeah.
Yeah, I mean, orthonormalization and orthogonalization, what is the difference?
I think orthogonal is different only.
No, I know the definition. I know that the difference in definition
I mean,
between ortho and ortho.
yeah,
What I'm asking
orthonormal
is, if you can produce an orthogonal basis, you can produce an orthonormal basis and vice versa.
Yeah. Yes.
Yeah, I mean,
Okay.
so you can take like a small space, like let's say P3 of X, like or maybe P2 of X, not P3 of X. You can take P2 of X, and you can try to find out an orthonormal basis using the Gram-Schmidt orthogonalization.
Yeah. Orthonormal, we should find.
Yeah.
We can find out orthonormal functions. Yes.
Yeah, basically find out some orthonormal function. That's right.
Yeah.
Think about this first question Q1.
I'm not aware of this affine function. How to find the number of steps required to convert the matrix into lower triangular matrix or upper triangular matrix. That's why I'm just I'm curiously know the details about on these things.
Converting a matrix into upper triangular or lower triangular matrix. That is what you ask.
The number of steps required to convert or something like that. Those concepts are new to me. I will look forward to those concepts. Yeah.
Okay. Okay. Let's discuss it next time.
Next week. Yeah. It's already 8 o'clock. Yes.
Yeah.
Okay, sir.
Okay. Yeah. Thank you for joining, everyone. I'll close the session here.